Already in the last lecture we had started studying chapter 8, and we were actually observing a procedure for orthogonalization of signals, and that was called the Gram-Simich procedure. And we were actually studying one example of how to apply the Gram-Simich procedure. So we saw that we had these four signals, and from these four signals, first of all, I obtained psi1 from S1 by just dividing psi1 by its energy, and you could see that its energy comes out to be 2. 1 square times 2, it is 2. Under root of 2, S1 divided by under root of 2, you will get psi1. Similarly, then you find psi2 for S2, but for that, first of all, you deleted the projection of S1 onto S2, and after deletion, actually you found it that once you take the dot product of S1 with S2, you can very well see it comes out to be 0. So there was no projection. You can see in the notes also. So the projection of S2 on psi1 was 0. So there was no need for any subtraction. So psi2 will be equal to S2 divided by its energy. And you could see its energy also comes out to be 2, and hence you will divide it by under root 2. Energy of this, it is also 2. 1 square times 1, and this also is minus 1 whole square is 1. 1 times 1 is 1. So overall energy is 1 plus 1 is 2. In this way you got psi2 from S2. Then for psi3 you have to take the projections of S1 and S2 on S3. So we took the projection C31. You can also call this S31, which means that this C31 or S31 means it is integral of S3 signal onto one signal. Similarly, this will be 3 signal onto 2, as we saw previously, that you were taking the projection of S2 on psi1 for C21. So for C31, projection of S3 on psi1, projection of S3 on psi2. So you could see if I take these projections, of S3 on psi1. So we have just found psi1 to be this is psi1 1 over under root 2 of S1t. So if I take the projection or take the multiplication of psi1 onto S3, so you could very well see it comes out to be minus and then plus, minus 1 over 2 into minus 1, this will become plus, and then 1 over under 2 times 1, this will be also become 1 over under root 2. So both will be added, 1 over under root 2 plus 1 over under root 2. So that is why you will get this as, this will be minus 1 times 1 over under root 2, this will become minus 1 over under root 2, and this will be 1 times 1 over under 2, this will become plus 1 over under root 2. So they will be minus 1 over under 2 plus 1 over under 2, and that will come out to be 0. So that is why C31 will be equal to 0. Similarly, for C32, you will take the projections of S3 onto psi2. So psi2 is like this. and S3 is like this. A minus part will go with plus part, will become minus, and this minus part will go with this plus part, this will become again minus. So this will be minus 1 over under root 2, again minus 1 over 2, this will become minus 2 times over 1 over under root 2, will become minus under root 2. So you can see C32 comes out to be minus under root 2. So you need to subtract. C31 is 0, so you just need to subtract C32 times psi 2 from S3. So subtract this from this becomes plus S3 plus, this is your D3 is equal to S3 plus under root 2 into psi 2. And so you can also draw, if you want to draw D3 here, just S3 plus under root 2 psi 2 means that in your psi 2 you just multiply it by under root 2. This will become 1, this will become minus 1, and you can add this to your S3. The 1 minus 1, this is 0, and 1 minus 1, this is 0. So this totally will go away. The signal will be only from 2 to 3. This will be your D3 signal. Then you need to normalize it, meaning its energy, and you know its energy will be from 2 to 3, height 1, its energy is 1. So this could come out to be 1. So your psi 3 will be just D3 divided by 1, which will be equal to D3. You could also do it like this, or in other words, you can also do it like this. You take its square, D3 square will be square, whole square of this into square of this, minus 2 times this to this. Okay, this I showed you in the last lecture. You'll be getting these values, and hence this will come out to be again equal to 1 from both the procedures. Similarly, you can calculate C41, which is the projection of S4 onto psi 1, S4 into psi 2, and S4 into psi 3. And let us calculate any one of them. Let us calculate C41, projection of S4 onto psi 1. So you can again see our psi 1 is like this, and I will take its projection with S4. So you know S4 is just 1, and this is 1 over under root 2. So the projection will come out to be 1 over under root 2 and height of 2. So you can see 1 over under 2 into height of 2, this will come out to be under root 2. Alright, this will be a C41. So you can check by yourself. The C42 will be 0 and C43 will be equal to 1. Again, you can see because your psi 3 is this signal, and multiplying this with psi 4, S4, you can see all of this is 0, so it will only exist from 2 to 3. Right? C43 will come out to be equal to 1. Now you can find your D4, which will be S4 subtraction of all the projections times their orthonormal basis functions psi 1 and psi 3, and you can see here that this comes out to be 0 because S4 is about 1. Under root 2 into psi 1, this will also become 1, so it will cancel it in the first two halves. Second half, psi 3 will be there, which is already 1, so it will cancel it from 2 to 3. So hence S4 will come out to be, the D4 will come out to be 0. So there is no reason that we should make another orthonormal vector because D4 is 0. So S4 is still a combination of psi 1 and psi 3. Hence your total vectors were 4, but your orthonormal basis comes out to be 3. So 3 vectors are more than enough, psi1, psi2 and psi3, to represent all these 4 signals. The 3 orthonormal bases which we have discussed before. Once you have defined your orthonormal basis, then you can very well see that you can write any of the 4 signals as sum of the projections of those signals onto the orthonormal basis. So this is, for this case, this is psi1 going from 1 to 3, 1 to 3. So any signal S1 to S4 can be represented by projections, and we have just calculated all these projections. Okay, for let us say this is S1, here we have calculated S1 1, then it will be S1 2, S1 3, and hence you will find in the notes it was C1, C2, no problem, you can just write S1 in terms of C, nothing, no change, just change of representation, both are same. So you can see what is SMN, same as CMN, projection of SM signal onto psi and orthogonal vector, or one of the orthogonal vector. Similarly, you can find the energy of any signal. Let's say I want to find the energy of this signal. So energy of this signal will be under root square of this thing. So it will be square of this whole and then integral. Now square of this whole means square of this and square of psi n. So your integral will just, this summation will comes out and your integral will be just around square of psi n, and square of psi n is always 0 for all the values of n. So you will just get sm1 square, sm2 square, smn square, or smn square n1 to n. So you are just adding after squaring up the coefficients of the dot products, and you will get the total energy. Similarly, we have seen that we can express our signals in terms of these coefficients. So we can represent them in terms of vector representation. You can write S1, S2 and S34 in terms of orthonormal vectors psi1, psi2 and psi3. And again, it is simple, we have actually done all those steps. Just to rephrase those steps, T is equal to the projections into the vectors, or the summation of the of each projection onto its vector. You can form a vector here and you can form a vector here. So their dot product gives you this sum. Now in the previous example, you could see that you had actually 4 signals, and those 4 signals will have these coordinates with respect to the orthonormal vectors. And you can see S1 was the first signal, and we found energy of S1 that was under root 2, and we found the orthonormal vector by dividing it by under root 2. So you could see that psi1 was just equal to S1 over under root 2. Just see previously notes. So psi1 comes out to be S1. This means that S1 is actually nothing but under root 2 into psi1. So S1 was totally represented by psi1 vector. It doesn't need psi2 and psi3 because all other vectors will be from S2 and S3, or those part of S2 and S3 that do not contain any projection of S1, so this will be orthogonal, so there will be no projection of S1 onto psi2 and psi3. So you can just write S1 as under root 2 psi1 as from here. So once it is clear, we can just write our S1 as under root 2, this will be under root 2 times psi 1, 0, 0 times psi 2 and psi 3. Hari, I hope all of you are understanding. हाँ जी, हमजा साहब समझ आ रहा है? रोल नंबर 172।
जी सर, आपका लेक्चर तो ले रहा हूँ, लेकिन बस थोड़ा सा लैगिंग की वजह से पूरा पिक नहीं कर पा रहा वो सर, इंशाल्लाह अगर टाइम हो रहा है।
अच्छा, right. So I actually also wanted to announce, as you should have seen the order by the registrar. So classes are being finished by the 2nd of July.
Yes sir, ऐसे ही है sir.
So yes, this means that we will not have 16 or 15 weeks of lecture. Rather, we will have less. So according to my calculation, it will be approximately 13 or 12 and a half weeks. So
बिल्कुल सर, इतने ही आ रहे हैं.
Yes, so I have indicated the course for the midterm after concentration with Dr. Tahir. So the midterm course will be till chapter 6. So we will be covering chapter 8 as much as possible. So whatever amount of 8 we can cover, that will be included in the course, as well as 7 for the finals. If you will go to the next chapter, then we will go include it in the finals. Otherwise, we will be having the course till the amount of lectures allowed by the university. Alright, so coming back.
मतलब कि सर आपसे ये पूछना था कि मतलब जिस तरह 2 जुलाई तक जो नोटिस आया है, आप तब तक लेक्चर्स कंटिन्यू करेंगे और जितना हम चैप्टर 8 कर लेंगे वो फाइनल में आ जाएगा 7 के साथ.
हाँ बिल्कुल ऐसे ही,
मतलब सर वो जितना भी कवर हो.
हाँ जाहिर जितना भी हो उसमें हम अभी तो चूँकि ना if you could remember that we have changed the course outline, so chapter 8 has been actually increased as compared to previous sessions. So that is why it is now more more lengthy. Previously it was taking about, I think, 5 lectures. So that is why this time we have put 7 lectures onto it. So if we just do the previous length as covered in the previous sessions, then we just require 5. So in that case, you can see that because today is the 18th, so 17 plus 5.
सर approximately 23-24 lectures बनते हैं, पूरा हो जाएगा अगर.
हाँ 22 तक. Even if we have 3.5, then we can still cover this 8th chapter, which is an important chapter. But it all depends. We might let us first of all complete the part that was in the previous sessions also. Then we can decide that whether that we should continue in this chapter or we can move on to the other chapters. But for this time, especially for the next 2 weeks, you can very well see that we will be spending time on this chapter 8.
Yes sir.
Thank you, sir. So coming back to the lecture. I was trying to explain you that all the 4 signals can be now represented in terms of the 3 orthonormal vectors, or your orthonormal basis, which consists of all the 3 orthogonal vectors. You are just representing your signals as a vector in terms of those orthonormal vectors. Let us now try to find the representation of S of 2. Again, in finding S of 2, we saw that there was no projection of S1 onto S2, so that is why it will be 0. S3 is still not made, and even it will be made, we know that all the projection of S2 will be cancelled, will be subtracted, so that is why this will be also 0. We will just have the projection of side 2 in defining S2, and you could see the energy of S2 is also under root 2. So if you could see previously, S2 just comes or psi 2 just comes out to be S2 over under root 2. You can see here S2 over energy in S2 under root 2. This again shows us that S2 is equal to under root 2 psi 2. In other words, psi 2 represents S2 with just a multiplicand of with just coefficient of under root 2. So S2 is given by under root 2 psi 2. So that is why you could see that S2 is just 0 under root 2 0. For S3, again, if you could remember, we saw that no projection of S1. All right, so that will be definitely 0. Then we saw, yes, there will be projection which was minus under root 2 from S2. S2 on psi 3 was giving us minus under root 2. And then the projection of S3 with respect to psi 3 comes out to be 1. ये आप चेक कर सकते हैं. This is actually projection of S3, or you can say projection of psi 2 onto S3 or S3 onto psi 2, and this we have also done here. C32. So same thing. It is S3 times psi 2, which we calculate to be minus under root 2. So that will be just minus under root 2. And yes, this is our D. This will be our psi 3. So you could see that psi 3 was just a signal from 2 to 3. This was your psi 3. It was just like this. So projection of S3 onto psi 3, these two parts will be 0. This part will multiply, and there, S3 is also 1, so it will be just equal to 1. If someone are not solved, you can just solve in a few steps by taking the projections of the respective signals S1, S2, S3 onto respective orthonormal vectors psi 1, psi 2, and psi 3. So S3 with psi 3 is equal to 1. Then representation of S4. This we have actually done completely, no need to do extra calculations. So you can see S41 is under root 2, you will get under root 2, S42 is 0, and S43 is 1. There is no S44 because only 3 orthonormal vectors are more than enough to represent all those 4 signals. That is why D4 was 0, so no need to have more orthonormal vectors. So under root 2 with S1 and 1 with S3 are more than enough to represent this. That is why it will be under root 2 times 1, S4. Now with these 4 representations of these 4 signals, I can represent them onto the vector space, to the vector space spanned by the orthonormal vectors. First of all, I draw the orthonormal vectors psi 2, I draw psi 3, and I also draw psi 1. And S1 was just under root 2 S1, psi 1 should be like this. You can also draw an arrow here because S1 is now a vector, or you can also not draw a vector because it understood that it is in the psi 1 direction. So S2 will be under root 2 into psi 2, so it will be of this much height. And we saw that S3 was a combination of psi 3 and minus psi 2, it will be like this. And S4 the combination of S1 with S3, so it will be a combination, will come right here. So in this way your vector representation of all the 4 signals has been shown. So This we have already seen all of this. Signal represented like this, and all of these projections are like this. Energy we have also seen, and we can represent each single waveform by this vector, which actually consists of which is an n-dimensional single space vector, where all these coordinates, they are just the projections of the signals onto the orthonormal basis or the orthonormal vectors. And you can also take projections of any of the two signals, and it will come out to be the dot product of their projections onto psi1 to psi2 psi3. So rather than going to the integral calculation, you can just take the dot product of the vector notation. Energy, this we have already seen. So s square can be written as projections s1 s2 s3 onto psi1 psi2 psi3. The projections will come out, and psi1 psi2 psi3, their square under root will come out to be 1. This will be a vector having projection on psi1 psi2 and psi3 with squares. So the energy is the square of the length of the vector, or equivalent to the square of the Euclidean distance from the origin to the point in the endum. Yes. So you can see here that energy of Sm was just equal to under root Sm vector whole square. So if Sm, let us say, is 1, 2, 3, it will be equal to under root 1 square plus 2 square plus 3 square under root, and then mod. So under root mod will cancel, and you just get 1 square plus 2 square plus 3 square. So you can just see that actually energy can easily be found once you have a vector representation. So you can take its mod square, you will get the energy, and so the orthonormal basis selection can change. For example, I have chosen from S1, then S2, and then from S3. I could have chosen, first of all, let us say, from S4. And hence the vector representation will also not be unique. However, you will see, even if you choose your orthonormal vectors from the same signal with a different order, the n value or the dimensionality of the signal space will still remain the same, even if you have changed the signals or changed as the order of the signals. Yes, you will be seeing that once you change the order, or you have different orthonormal bases for the same signals, then the new signal space will be actually the same signal space, just moved by some rotation angle. For this, let us look at another example. Again, we have those 4 signals previously which we started with, and we have the orthonormal set functions in 8.1b. Achha. Here is showing those vector representation which I have just told you here. These were the vector representations. We just calculated all of them, and this was its representation in vector space. So again, he is doing the same thing. He is just calculating S1, under root 200. We have just shown, which is equal to under root 200. In this way you can calculate all of them as you have just shown earlier, and hence this will give you the values of the same representation as we just told you earlier. It's the same diagram which I have also shown. Now what we do, as we said that basis functions is not unique. Let us say we use another set of basis functions. For the same example, we use another set of basis functions. Alright. And again we will calculate your projections of S1, S2, S3 and S4. So you will get these projections. Let us just check. Let us calculate for S1. You know, S1 was a straight signal from 0 to 2, and projection of this S2 onto this will be just 1. The projection will just give you 1. That is why you can see it will be 1. Similarly, projection of S1 with the psi 3 will be 0, because the signal of S1 was only from up till 2 time, and this is after 2 time. And similarly, you can also check projection of S1 onto S2, or you can say, all right, S1 onto psi 2. S1. So S1 was from 0 to 1 onto psi 2. Again, you can see it will give you 1. So you just put 1 here. And projection of my S1 signal onto the psi 3. You can see that because psi 3 was from 1 to B. So projection of psi 3 onto projection of S3, you know, which was this was your S3. All right. So it was -1 and then 1. So projection of S3 onto psi 2 that we have done. Projection of S3 onto psi 3, you can of S1 onto psi 3. So you can see this is 0 0, so it will give you 0, because it is only extending up till 2, while psi 3 is extending from 2 to 3. So that is why their dot product will be 0. Alright. So in this way you can find the representation of all the vectors with different orthonormal basis functions. For example, for S4, you can see S4 was a constant signal from 1 to 3. So it will have 1 here, it will have 1 projection here, again it will have 1 projection with respect to psi 3. So you can just calculate. So you know S4 comes out to be 111. So and you can basically check that again. You just require 3 orthonormal vectors to represent the 4 signals. The dimensionality does not change with the change of orthonormal vectors. Again, you can see that the length of the vectors or the energies, they do not change. And the change in the basis is essentially a rotation or reflection of the signal points around the origin. So you can see here, for example, its length, you can see it is under root 2. Okay, and previously for the original basis function you can see that S1 was also under root 2, S2 is under root 2. Here you can also see that S2, which is equal to this one, this energy will be under root 1 square plus 1 square will be under root 2. So again this shape would not change. The lengths will not change, And yes, the points could be rotated or reflected, but the lengths will remain the same. For example, you can see the S3 and S4, their representations gives you the length of 3 for this orthogonal base. And for the previous one, you can also see that SC and 4 they were also under 3. So the lengths are not changing, but yes, the positions are changing. You can say there is a rotation or reflection. So Gram's image, yes, it gives us an orthonormal basis for representation of the signal sets, but in many cases you can just observe the signals and you can make up your orthonormal set. You don't have to follow the procedure, but if you follow the procedure, definitely you will get the correct orthonormal basis. Now, after setting the representation of any signal onto the orthonormal basis, and then its representation in terms of vectors, its energy and its positions. So now we go to some of the schemes or methods that are used for binary modulation. So binary means two. So there are two types of different signals. Uh, so you will see all these examples. Basic signals are binary antipodal and binary orthogonal signaling, and the other schemes are actually uh, special cases of antipodal and orthogonal signaling. So you can see here we will be studying these schemes, and the data, as we have already learned in the last chapter, that you have converted them into some of the quantized values, and those quantized values are just represented by a sequence of zeros and one. So your bit rate is RB, which actually is equal to the sampling rate, Nyquist rate, or let us say the sampling rate times the number of bits which are used to represent the each quantized value or each encoded value. So first is binary antipodal. In binary antipodal scheme, so we have one signal that is used to represent so we have just in this scheme the information bit is 1 and it is just represented by a pulse pt of duration t, and the information bit 0 is represented by the same pulse but by negative of that pulse. That is why it is called antipodal, because representation of the 0 is antipodal to the representation of 1. Antipodal. So the duration of this pt is again tb. So the duration you can see is equal to TB, where TB is the also the interval for the bit. So each 1 or 0 is just represented by a pulse, and the pulse duration is the same as the duration of the bit. An example is here. So we have two signals. You can see that both signals can be represented by one bit representation. Yeah. So where you have just PT with A, this will become S1, and PT with minus A, this will become S2. This is called antipodal. So both the signals are negative to one another. This is also called binary pulse amplitude modulation, because you can see that both the signals are transmitted by the amplitude of the pulse. So pulse is 1, but you can change the amplitude from A to minus A, and this will also be called pulse amplitude modulation. Pulse rate was RB, as every bit is taking TB time, so our rate will be 1 over TB. You can see TB was the interval. So in case of binary pulse amplitude modulation, if you could remember, we started with binary antipodal, but we can also call them binary pulse amplitude, because you can see that you have the same pulse and you are just differentiating the pulses with respect to the amplitude. You can also call them binary PAM. So it can be represented as SMT into AM times GT, and AM can take two values, AN minus A, and G is the rectangular pulse is the unit amplitude as shown in figure 8.5. So again, some of the steps, they are missing, so I also couldn't find the explanation in Dr. Tahir notes, so I will just show you my notes where there is no confusion. So again, you can see that you had these two signals. You had S1, which was A from a TB duration. This was S2, which was again of TB duration, but its amplitude is minus A. So you're differentiating with respect to the amplitudes. You can also call it binary palm. So first of all, I find its energy. So its energy will be square and integral. So A square times TB will be its energy. Hence my psi 1 from S1 comes out to be S1 divided by energies under root. This comes out to be S1 over A over under root EV. Similarly, you can calculate ES2, which will also come out to be, this is minus A square will become A square into TB. So hence your energies of both signals are the same. So yes, psi1 was calculated, and you can see that the energy in both the signals is equal to A square into TB. So I can write A as equal to under root TB or EB over TB. You can say it is ES, but you can also say it is EB, because you can say, or epsilon B, because energy in the first and second signal is equal to the bit energy, because one signal is just representing the bit interval, the bit energy. The bit energy is A square TB, hence A can also be written as under root TB EB over TB. This is your psi1. Alright, so our psi1 we just saw, it will be equal to S1 over A over under root TB. S1 was having an amplitude of A, so A divided by A, it comes out to be 1, and the amplitude comes out to be 1 over under root TB, the height. So this will be our psi1, will be just S1 divided by A over under root TB. So you know S1 was of height A, so A divided by A, this will become 1 divided by under root TB, so will become of height of 1 over under root TB, and width will remain the same as before, which is TB. So as you can see that psi1 can represent both S1 and S2. S2 is just the same psi1, just multiply with the negative. So psi1 can become the single orthonormal basis, and let us denote it by psi t. And you can also calculate the projections of S1, S2, which we have already discussed. S1 is the projection of S1 onto psi, S2 projection of S2 onto psi, because one psi is enough, so you don't have to do further. And projection of S1 onto psi, you can see this comes out to be A over under root TB. The height of S1 is A and height of under root T is 1 over TB. It will come out to be product of A 1 over TB, and the width of the existing is TB. So you know it cancels, comes out to be A over under root A into under root TB. Similarly, you can find for S2, its amplitude will come out to minus under root A over TB. So I can just draw them. S1 is equal to A under root TB and S2 is equal to minus A under root TB. But I also know that A is equal to under root EB over TB. So if I put the value of A here, TB TB cancels, this will become under root EB. This will become minus under root EB. So this is also the vector representation of this will be the vector representation. You can also write an arrow, but you can also write it without the arrows. They both are the same. And hence you represented your antipodal signal. And you can see in antipodal signal, we have the same basis, that one signal is 180 degree phase shift with the other signals, and the lengths of both of them are the same, which is under root EB, or its energy will be equal to EB square. So we have done all of this from the notes, so no need to. Again, you're seeing here one way is that you draw these arrows to show it's composed of psi1 and psi2. Other thing is that you basically yes. Any question?
Here, please put some balance 100 rupees. Number okay 03 1010.
I think Mohammed Zishan, do you have some question?
Wrong number 424895.
Actually, I think someone was talking to someone else. All right. So you could see I have also clarified in the notes that you can represent them. Another example the book has done, and for this example again you have these two signals. Again you can notice that this signal is antipodal of this signal, because this signal is exact negative of this signal, exact negative of this signal. You just multiply by -1 and you will get this signal. So again you can very well see that these are both antipodal signal. You will have just one orthonormal basis that can easily be found by dividing this signal by its energy. So again, some of the steps were missing. I just have done it for you. So these are the signals S1 and S2. I just took S1 and I divided it by its energy. So I calculate its energy. So its energy, will be square of the amplitude times the time interval Tb over 2, and again square of the amplitude times the interval Tb over 2, and the energy comes out to be Eb. Alright, so I divide by under root of Eb, and I will get my psi. So you can see that your psi 1 or psi will be just dividing by Eb. Eb cancels, and you have this will be your psi. And this full psi will be also sufficient to represent S of 2. So one orthonormal basis will be more than enough. And here I have also calculated the projection of S1 onto psi t, S1t onto psi t, and you can see it comes out to be under root Eb. Because for psi t, for the first part, it is 1 over under root Eb, this is Eb over under 2b, this S1, interval is Tb over 2. So you can see all of it cancels, and then half of plus 1. So the projection of S1t onto psi t comes out to be under root Eb. And you can also see from here S1t is equal to under root Eb into psi, or under root Eb into psi 1. So under root Eb is enough for it to be represented. And you can also calculate for S2. You can very well see it comes, if I project S2 onto this, so it will come out to be minus under root Tb. So under root 2b and minus 2b will represent our signals, and it will be the same representation as the representation of the previous antipodal signals. The same representation we will get after representing these two signals. And S1, S2, they all again come out to be under root Eb and minus under root Eb. So very important result, that any pair of antipodal signals, they will be always a pair. One has to be negative of the other. They can be represented geometrically as two vectors on a real line. One vector is a negative of the other, and the unit energy is given by Pt over Ep. Ep denotes the energy in Pt. But we have just seen that it is very simple. You just take signal S1, or you can take the signal S2, and you will still be able to find your So we have seen this in detail. You just take its energy, divide energy with the first signal or the second signal, you will get your orthonormal function. Another scheme which is called binary amplitude shift scheme. So this was not available in the notes, but was given in the book, so I said why not also cover this. And in binary amplitude shift keying, it is actually based on the same binary antipodal or binary amplitude modulation. A little bit difference is that you also have the carrier signal. So again, you have two baseband signal plus minus PT, which again, just like antipodal signal, and they are being used to amplitude modulate a sinusoidal carrier. So this was my S1, this is given, and this is my S2, and where PT is the rectangular pulse. Of amplitude comes out to 2 EB over TB. This we have actually already seen here, that this pulse is of length 2, So S1 is this signal and S2 is this signal. Again, we need to find its orthonormal basis. So it comes out to be this thing, and again some of the steps are missing, so I would like to show in my notes. So how to find the orthonormal basis? First of all, we have to find its energy. So its energy comes out to be, but let us check. So this was the signal. Square, under root cancels, and this becomes cos square. Cos square becomes 1 plus cos 4. But here we make sure that this FC is multiple of 1 over 2 TB. Alright, so this means that if I have 2, because this is 2FC, so 2FC will be equal to 2 cancels, FB, this is a mistake here, this FB will be 1 over TB, so K over TB. So your frequency in this is actually made sure that there is actually multiple to the highest. You can see here A2FC is actually having multiple of 1 over TB, so it has more than TB intervals. Alright, that is why this cos 4 will have enough time period to cover its whole cycle in this TB time. Alright, so that is why this cost will go towards 0. Alright, and hence energy comes out to be EB. So your orthonormal function is again same principle, S1 divided by 100 EB, and S1 was 200 EB, this comes out to be 2 over TB cos 2 pi FCT. So we have in effect find this value, which I've shown you in my notes, and these are the binary ASK signal waveforms. Written how to find psi S1 divided by 100 EB. Hence your psi will be found. You can find the projections of S1 and S2 onto psi, which you can very well see is under root EB. So the same diagram will be more than enough and these signals under root EB under minus under root EB. So you will ask that if alright their vector projection is same, then what is the difference? The difference is that our orthonormal basis is changed because you have 2 pi FC. Alright, so the spectrum of your signals is actually changed. It has been modulated FC frequency. So he says that the low pass signals, we know what their content is around F0, while the high part contents in this binary ASK, their spectra will be located around FC, because you can see it has been modulated by cos 2 pi FCT, so it will be going around FC. Next is binary orthogonal signaling. Binary orthogonal signaling is also the basis of binary pulse amplitude modulation. So in the notes only binary pulse amplitude modulation is discussed, and this is not discussed, so I think this should also be discussed, so I'm just discussing it as in the book also. So binary orthogonal. what is the meaning? In binary orthogonal, we deliberately make the two signals uh, orthogonal to one another. That is what is called binary orthogonal signaling. This is done deliberately. Energy of S1, S2 will be again the same. Let us say it is EB. You can calculate its energy if it is not known. And then they are orthogonal. Orthogonal means that S1, S2, they are 0. This means that you will now require two orthonormal bases, not one, as was required for antipodal schemes. For amplitude shifting here, it will be different because the two vectors are orthogonal. This means that you will require two uh, orthonormal bases or orthonormal vector, and psi will be S1 over delta EB and psi 2 will be S2 over under root EB. So you can see that S1 is given by under root EB psi 1 and S2 is given by under root EB psi 2. And you can see here that as they are orthonormal, so their representation will be EB, EB, and they will be orthogonal to one another. This is with arrows and this is without arrows. So S1 is under root EB 0, S2 will be 0 under root EB. Because their dot products with the other will be orthogonal, hence it will have 0 representation in the other dimension or the other orthonormal vector. Now, based on this orthogonal scheme, we will have actually binary pulse position modulation, which is an example of this orthogonal scheme. So in this scheme again we have two pulses, but those pulses are different only in their locations. So binary pulse position modulation is an example of binary orthogonal signaling. Again, we apply two pulses in a way that they are orthogonal to one another, so we put them in different locations. The signal forms S1 and S2 are there, but you can see that they are inherently orthogonal to one another because first ends at TB over 2 or the second starts at TB over 2. So their dot product will be 0. Alright, so though we saw them, these two signals are here and you can see they are non-overlapping and they are orthogonal, so their dot product will be 0. And you can find the energies of S1, S2, and you can see the energies of this will be square of this, so 2 EB TB times TB over 2. So it will cancel, it will come out to EB, this will also come out to be EB. Energy, this will be 2 EB TB. Once you take it square, TP TP cancels, and you can see that this comes out to be yes, TB 2 EB over TB times TB over 2. So 2 and TB cancel, it comes out to be energy EB. Same thing you can check here, energy comes out to be EB. Here again you will have two orthonormal vectors. You can see the duration, they exactly match with S1, S2, but their energies are normalized because you know the energy comes out to EB, you will just divide by EB energy. This will be 2 TB and so we can represent them as this thing, S1 as projection of psi 1 to psi 2 and S2 as projection on psi 1 and psi 2. And you can calculate all these factors, you know, two of them will be zeros, only S1 and S2 will exist, and you can calculate them, it comes out to be under root EB. Rest of them will be 0 because they are orthogonal. S1 is psi 1 which is orthogonal to S2, and S2 is psi 2 is orthogonal to psi 1. So the two signals are represented two-dimensional vectors and are shown in figure 8.1. This was, you can see the same orthogonal scheme is quite apt to represent binary pulse amplitude modulation because they are orthogonal schemes. This was binary pulse amplitude modulation that we have already seen that they are on the same orthogonal basis. And this was actually, you could see, orthogonal. So we have again two different signals. And you can see that S1 and S2 are again S1 and S2 are again, you know, they are again orthogonal to one another. You can check, this comes out to be 0. And you can again find its psi 1 and psi 2. Normalizing S1 by the energy. Energy, you can very well see EB. So its energy will come out as this, and energy of psi 2 will come out to be like this. Just dividing by EB, you will get this thing. So if you have any questions, you can ask. So we have actually covered till binary pulse amplitude modulation. You could see that just can choose two orthonormal bases, and we will be studying this frequency shift keying in the next lecture. So example we can also do in the next lecture. So if you have any questions, you can ask. All right. So I will end my lecture here. Uh, at this point, so we shall start with binary orthogonal signaling. We will start with binary pulse amplitude model that is also being covered, but I will also try to again explain you with help of these notes also, so that we have covered it with respect to the notes as well as the book. This was your binary pulse modulation. You can see that both signals are orthogonal by themselves. This is the main criteria. In that case, you have to choose two orthonormal bases, and they can be easily chosen by just finding the energies and dividing it by the energies EB. So you will get these two as the representations. It just comes about by dividing these two signals by EB, which was the energies, under root EB, and you will get these two signals. These are the original signals, and these are your uh, orthonormal bases, 2TB, 2TB. Once you have the orthonormal bases, then you can very easily find all the projections, S11 projection of S1 signal onto psi1, S12, and like that. And you know here, two of them will be zeros because this is an orthogonal scheme. Only S11 and S22 will be there. You can see here S12 and S2 will be 0. Only S1 and S2 will come out, and that will be equal to under root EB. This will be your projection, this will be your representation, and you can very well write it like this. So for this is also simple, and again the main thing is always to check whether S1 and S2 they are orthogonal. Once they are, you can see again they are orthogonal. Once they are orthogonal, no problem. You have to choose two different orthonormal functions. All right, I will end the lecture this way. Again, if you have any questions, you can ask. Thank you very much.